Okay. Let's go ahead and look at this next problem that we have here. The Thevenin and Norton circle, and they want us to find the power if the load resistance, if our load is 5 ohms. Okay. So power. They give us this circuit here, and we have 2 sources. Okay. We've got this battery and then this current source. So we need to find the Thevenin source. So we need to find R Thev and V Thev. So step 1, there's no dependent sources. And I don't see any diamonds in there or anything, so we're good. Step 2, sorry. So therefore we'll zero out our sources. So we'll turn the battery into a wire, and the current source into an open terminal. Okay, so if we go and do that, let's go and draw that out. Bam, bam. That'll be 10. This will be 5. Okay, there we go. And we'll go and drop our plus minus. This is VOC. Remember, we're going to act like this is a battery pumping current into the circuit, and we'll find the equivalent resistance going that way. All right. So we see that from here, where we this is where that battery was, and this is where the current source was. But we see that that's a wire that's not clipped out. Those two will be in parallel, so our parallel will equal 10 times 5 over 10 plus 5. That'll give us 50 over 15, which is 3.33 ohms. Okay. And that's going to be our R Thevenin because it's only going to be one resistor. Okay. So first part right there. Now we define V Thevenin. So to do that, so step 2 was find R Thev, which is what we did. Okay. Step 3, find V Thev or I Norton. Okay. So to do that, you need to jump back. For step 3, we need to jump back to the original circuit. And jumping back to the original circuit, if we know that this is VOC, I need to find the voltage at that point, which is the same as voltage there, voltage there, voltage there, and voltage there. And what it is that we're trying to find the voltage drop across those terminals, right? So looking at this problem, if I know voltage along a wire is the same, if I know the voltage at this point, I know the voltage at that point, which is the voltage at that point. So now what I'll do is looking at this, if I go and drop a ground right there, where V of G is equal to 0 volts, I can treat this as a nodal analysis problem, all right? And what we'll do is we know that our current will come in from this side. That'll be our 1 amp. We know act as if some current's going down this way, and then we'll have some current going that way. All right. So let's go ahead and do that. So I'll call this V1 right there. Okay. So let's go ahead and write all that out for us. So V1 minus 10 over 10 plus V1 minus 0 over 5 minus 1. Okay, and that will equal 0. So what it is we know that 1 amp is going to be entering, so we'll just make it negative, but we assume the 2 other currents are leaving. Okay, now all we need to do is go ahead and simplify down. So we'll do this. We'll do 1/10 V1 minus 1 plus 1/5 V1 minus 1. That's equal to 0. Simplify that down a little bit more. So that'll be V1 3/10. Right. And that'll be equal to 2. So therefore, V1 is equal to 20 over 3, which is equal to 6.6. Yeah, 6.67 volts. And we know that V1 is equal to VOC because it's along the same wire with no elements between, right? Because there's no elements there to suck up any voltage from anything, so we can just say that VOC is equal to 6.67 volts. All right. Okay, so if we go and draw that out, we can do this. Let's do plus minus. Do VThef. Right. This will be RThef. Now, here I'll write RThef. So 3.33 ohms, and VThef is at 6.67 volts. Okay, but they said, well, what if we went and added a load resistor here, RL, which is equal to 5 ohms. So if we do that, what we'll need is to find the current through everything, okay? So what we need to do is to find this current, which is the current through the load, because now the wire's closed and it's going through that resistance. So I of L will have to be equal to V Thevenin divided by R total, right? Because it's all the resistance on that branch. So it'll be 6.67 volts over 3.33 ohms plus 5 ohms. Okay. And what will that give us? Looks like that gives us 0.8 amps for I load. All right. And now we can, so there's a couple of ways we can go about solving for the power. So the power we know is equal to VI, where we have the current, but we don't have the voltage. And to go solve for the voltage, that would take a couple extra steps. But we also know power is equal to I squared R. So all these mean load, by the way, the L's. So I'm just dropping here. So by doing that, we know the current, we just solve for it, and we know the resistance, so we can just plug those in. So the current is 0.8 amps. Let's square that. our load was 5 ohms, so that'll equal 3.2 watts. That'll be power of the load resistor. Okay. Just basic Thevenin and Norton problem. So just make sure that you know all the rules, the 3 steps that we had at the top there, and know what a load resistor is, because they can pull that out and use that on the exam.